Hello everyone, welcome to this video. Today we're going to talk about closed loop compensators, PI versus PID. In this video we will see the introduction first, then we will show the PI compensator that we are going to use to operate a buck converter in closed loop. We will design a PID compensator to try to improve the response of the converter in closed loop. And finally, we will show a comparison between both compensators using Qspice simulations. These are important videos related to these topics. In this video, Qspice number 7, we saw how to do the closed loop frequency response of a DC-DC converter. In this video, we showed how to design a PI compensator for a DC-DC buck converter. Qspice number 4. In this video, we showed how to do frequency response analysis of DC-DC converters in Qspice. And in this video, Qspice number 5, we explained how to obtain the closed loop frequency response of DC-DC converters, and we will be using this methodology in this video today. So this is the converter that we have been using in these previous videos. It's a buck converter. Here we have all the information. We are measuring the output voltage. We are using here a PI compensator to operate the converter in closed loop. This is a PWM modulator using a comparator comparing the output of the compensator with a ramp of 10 volts peak to peak, and then the output of the PWM comparator goes to the switch. So in this video, Qspice number 7, we used a PI compensator with this expression here and this transfer function to implement the closed loop operation of our converter. So let's remember how we designed this compensator. So here we have the block diagram of the small signal transfer functions of the different blocks. Here we have the compensator. This is the response of the PWM modulator. This is the response of the buck converter. This is the duty cycle. And here we have the output voltage. We are measuring the output voltage with a sensor which has a gain equal to 1, and then sending this to be compared with the reference and sending the error into the compensator. So here we have the response of these two blocks that includes the gain of the PWM modulator times the gain of our buck converter. So this is the response in red. We have a double pole here at the resonant frequency of the LC circuit that we have in the buck converter, and this is the 0 corresponding to the ESR resistance of the output capacitor. So what we have done is to place the 0 of our compensator, here is the response of the compensator in blue, and the 0 of this compensator is at the same frequency as the double pole that we have in the buck converter. So at the end, in green, we have the response corresponding to the loop gain. So it is the product of all the blocks that we have in the loop. And therefore, what we get is that the loop gain crosses 0 dBs at this same frequency, the frequency of the poles that we have in the buck converter, which is around 7 kHz. And because here we come with minus 90 degrees due to the pole that we have at the origin, and when we reach this point here, we have another minus 45 degrees due to the effect of this pole here. So in total, the phase of the loop gain is minus 135 degrees, which means that we have a phase margin of 45 degrees. So we designed the compensator making this part, this gain here, equal to 0 dBs. So the ratio of both resistances is equal to 1. And the other condition is that the frequency of the 0 has to be equal to 7.1 kHz. And from this we can get the value of the other components. So we can fix the value of the capacitor C2 to 10 nanofarads and then get the values of R2 and R1 as shown here. Both are equal and with a value of 2.24 kiloohms. But in order to have a more accurate information about the behavior of our system in closed loop, it is better always to do a mathematical study of the system, because when we do the design manually, as we have shown in previous slide, we are working with linearized responses of the different blocks, but in reality we know that the responses are asymptotic. So here we have used WinPython to do the analysis. We have the different transfer functions of our system. Here we are doing the plotting of the different transfer functions, and then we are showing here in this part the different responses. In red we have the response of the PWM modulator and the buck converter. So we have the response here in red. In blue we have the response of the compensator as shown here, and then in green we have the loop gain of the system, so it's the product of all the transfer functions. So we can see how in green we have this response that is going to cross here 0 dBs, and at this point we have this phase also for the loop gain. So if we analyze this, we can do this very easily in WinPython, because we have this function here, margin of t, and we can get all the parameters. The two that we are using now are the phase margin and the crossover frequency of the phase. So with this we get the information that we want. So the bandwidth frequency is around 5.1 kilohertz and the phase margin is approximately 54 degrees. So we get this, the bandwidth that we have in our system is 5.1 kilohertz. The switching frequency of our converter is 200 kilohertz. So we can get that the bandwidth that we have in our system is the switching frequency divided by 39, almost 40. So this is quite conservative design. Our question is, can we increase it? Can we increase the bandwidth of our system using this PI compensator? Or do we need a better compensator like a PID compensator? Let's take a look at this. At the end, in our PI compensator, we have only two parameters. One is the frequency of the zero, and the other is the gain at high frequencies, the gain in this flat part of the response. So we can try to change the value of these two parameters to see what is going to happen in the response of our converter in closed loop. For example, here we are showing the response when we decrease the frequency of the 0 to 1 kilohertz. In our design it was 7 kilohertz, now it's 1 kilohertz, and then we have this response for the loop gain. So of course the loop gain crosses 0 dBs at lower frequency, so the bandwidth is going to be lower. Here is around 1.8 kilohertz. The phase margin increases, but in any case we are making our system slower. The other possibility is to change the gain at high frequencies. If we decrease this gain to this value, for example 0.1, which is equal to minus 20 dBs here in this part, again, what we are going is to make our system in closed loop even slower, because the bandwidth frequency is decreasing. The phase margin increases. In our original design it was 45 degrees, now we have 65 degrees, but the system is slower. So to make faster our system in closed loop, we have to go in the other direction. If we increase the frequency of the 0 here up to 10 kilohertz, then of course the loop gain is going to cross 0 dBs at a higher frequency. For example, here we have 8 kilohertz, but the phase margin is very small, so we are very close to unstable behavior, so this is not a good design. The other possibility is to increase the gain at high frequencies. by changing here the value of the constant Kc equal to 10. So here we have 20 dBs in this part. And then we have a much higher bandwidth frequency, so almost 20 kilohertz, but the phase margin again is quite small, so we are going to have a quite underdamped system. The overshoot of our response is going to be quite high, and we are again quite close to the unstable behavior for our closed loop. So the conclusion, as we can see, is that it's difficult to improve the response of our system using a PI compensator. So let's see now what we can do by using a PID compensator. So here we have the typical implementation of a PID compensator using an operational amplifier. We are adding some new elements here in parallel with R1. We are adding resistor R3 and capacitor C2, and in parallel with the network R2 and C1 we are including another capacitor C3. So if we analyze the response of this compensator, we will get this expression here, in which we have everything. We have a pole at the origin, so we are able to make zero the error at steady state. We have two zeros and we have two poles, and with this factor here we can control the gain of our compensator at the different frequencies. So this is the complete response of this schematic here, but usually in order to simplify we can do like this. We can choose capacitance C1 much greater than capacitance C3, and this is possible as we are going to see now, and with this we can approximate this factor approximately equal to C1, so we get this expression here, much simpler. And here, because C1 is much greater than C3, we can approximate this value to C3. And then we get this expression, which is much simpler. Here we have the values of the two zeros and the two poles, and C1 can be much greater than C3 if we do the frequency of the pole 2 much greater than the frequency of the 0, 2. So if we represent the response of the compensator here as a function of the frequency, then we will get the pole at the origin, then we have the 0 number 1, we get the 0 number 2, then we get pole number 1 and then pole number 2. The level of the gains here is this value, and the level of the gain here is this other value. So in order to make this expression valid, we have to make that this 0 number 2 has to have a frequency much lower than the pole number 2, which is easy to achieve. But today we are going to use even a more simple implementation of a PID compensator. What we are going to do is the same implementation, but we are going to locate both zeros at the same frequency and both poles also at the same frequencies. So these are the conditions that we have. The zeros are going to be located at this frequency, the poles at this frequency, and we have these other two conditions to fulfill to implement the design. And of course, the frequency of the poles has to be much greater than the frequency of the zeros because of the condition of C1 much greater than C3 that we have seen in previous slide. So this is just a degeneration of previous compensator in which we are locating both zeros and both poles at the same frequencies. So now let's see what we can do with this PID compensator to improve the behavior of our buck converter in closed loop. Let's see first what we can do with this new compensator We have expressed here the compensator with this gain Kc, and then we have the frequency of the zeros and the frequency of the poles and the pole at the origin. So imagine that we placed both zeros at the same frequency as the double pole that we have for the buck converter. Then these two zeros are going to compensate the effect of the poles of the buck converter. So the loop gain is going to come with a pole at the origin. So it's going to have a slope here of minus 20 dBs per decade, and here there is no effect of any zero or any pole, so the gain is going to continue at minus 20 dBs per decade in this area also. And now if we place these two poles of our compensator at the same frequency as the zero that we have due to the ESR of the output capacitor, then at this point we are going to have only the effect of one pole, because one pole here is compensated with one zero here. We have the effect only of one pole, so we have a pole at this point, and therefore the slope of the gain is going to increase up to minus 40 dBs per decade. But at this point we are going to have a phase of the loop gain equal to minus 135 degrees. So now the other parameter that we have in our compensator is the parameter Kc. So we can modify Kc and move up or down the loop gain response, so we can adjust the bandwidth that we want. Imagine that we increase here Kc, so the loop gain is going to move upwards. So we will be able to locate this point at 0 dBs here, having a phase for the loop gain of minus 135 degrees, and therefore we could get a phase margin of 45 degrees. So with this design we can get a bandwidth equal to the frequency of the ESR 0, which is 106 kHz in this design, and at this point keeping a phase margin of 45 degrees, so the system would be stable. The problem is that a bandwidth of 106 kHz in our design, in which we are operating at a switching frequency of 200 kHz, is a very high bandwidth because it represents the switching frequency divided by 2. So it's quite risky because we are getting very close to the switching frequency. This means that we are including in our loop changes of the duty cycle that are close to the switching frequency divided by 2, and this is too close to the nonlinear operation of our converter. We usually need to make our system stable and operating in linear region that the duty cycle changes slowly compared with the switching frequency. So now that we know what we can do, we are going to do the design mathematically and try to find a better design for our converter operating in closed loop. Here again we have the WinPython script, now with the new expression for our compensator, and again we have here the different transfer functions, and we can see in blue the transfer function corresponding to the compensator. What we have done, as we have seen before, is to place the two zeros here at the double pole of the buck converter and the two poles at the same frequency as the ESR frequency. And then we have adjusted the parameter Kc shown here to this value 1.5 times 10 to 5. So with this, as we can see, the loop gain has a crossover frequency of around 20 kHz and the phase margin is 80 degrees. So with this PID compensator we are getting a higher bandwidth 20 kHz in comparison with 5 kHz, and even a better phase margin, 80 degrees in comparison to 45 degrees using the PI compensator. And this is the design of the different elements for the implementation with the operational amplifier. So the frequency of the 0 is equal to 7.1 kHz, equal to the frequency of the double pole of the buck converter. The frequencies of the poles of the compensator is equal to 106 kHz, which is the frequency of the ESR0. The gain factor, which is given by this expression here, is equal to 1.5 10 to 5, as we have seen. And then we have these two other conditions, as we saw in previous slides. So then we have 5 equations, 6 unknowns, so we can choose, for example, C2 equal to 10 nanofarads. This is the easier way to do it, because now directly from this equation here we can get R3, from these equations here we can get R1 plus R3, and then knowing R3 from this other equation we can get R1, knowing R1 we can get C1, then from this equation we can get R2, and from this equation we can get finally C3. So these are the values that we get. All these are reasonable values to be implemented with an operational amplifier. This is 2.1 kilo ohms, this is 7 kilo ohms, this is 150 ohms. This capacitor is 3.2 nanofarads, approximately 10 nanofarads, and 213 picofarads. So with this we can do the implementation of our compensator using an operational amplifier. Now, before testing our compensator in closed loop with the buck converter, let's do a simulation of the compensator itself to check that everything is okay. Here we have the operational amplifier. We have selected now an almost ideal operational amplifier with a very high DC gain, a very high bandwidth. So the behavior of the operational amplifier is not going to affect the behavior of the compensator. We have studied how to analyze the effect of the response of an operational amplifier in the response of the final compensator in previous video, but today we are going to consider an ideal amplifier for simplicity. So here we have the different values, and we are doing an AC analysis. We are injecting here an AC signal of 1 volt, and then to correct the minus sign of this implementation, we are using this voltage source. So we are multiplying the output by -1. So in this way we can represent the exact behavior of the compensator without considering the minus sign that we always have in the loop. So now we can run the simulation and see the results. And here we have the results of the simulation. This is the gain of the compensator. So we have the response of the pole at the origin, then we have the two zeros at this point, the two poles at this point. We can see that the phase at low frequencies is -90 degrees, which corresponds to the pole at the origin, and then we have an increase in the phase, which is the typical behavior of a PID compensator. This is the boost in the phase that we need to make our system stable with a higher bandwidth. So everything is okay. Now we can test our compensator in closed loop. Now we are going to operate our converter in closed loop, and we are going to plot the loop gain of our converter using the PID compensator that we have just designed. For this, we include this voltage source here in the loop, as we have seen in other videos, and we are modifying the amplitude of the perturbation. If we are at low frequencies below 50 kHz, the amplitude is going to be 0.2 volts, and at frequencies higher than 50 kHz, the amplitude is going to be 0.3. I have tested several values and then trying to get the better response for the loop gain. So here, as we can see, we are doing a transient analysis up to the steady state operation plus 6 times the switching period of each perturbation. We do this at several frequencies and then processing the information and so on. We have seen how to do this in these previous videos, Qspice number 4 and Qspice number 5. So if you are not familiar with this process, please take a look at these videos. So now we can run the simulation. And here we have the result of the loop gain. So as can be seen, is as expected. We can measure maybe the crossover frequency at 0 dBs, approximately like here. We can see that we have a crossover frequency of 20 kilohertz and the phase is minus 100 degrees. So we have a phase margin of around 80 degrees as we have calculated in the theoretical design. And now what we are going to do is to test both compensators operating in closed loop with the same converter, with our buck converter. Here we have the PID compensator with a bandwidth, as we have seen, of 20 kilohertz and a phase margin of 80 degrees. And here we have our PI compensator with a bandwidth of 5.1 kilohertz and a phase margin of 54 degrees. What we are doing is a pulse at the input, so we are going to increase the input voltage. We're going to do a step-up transient at the input voltage, increasing the input voltage in 2 volts. Same situation here. And then in this way, we are going to be able to compare the output of the converter with a PID compensator and the output of the converter using a PI compensator. So now we can run the simulation, and here we can see the response of both compensator. In blue we have the response of the PI compensator, so we are getting a steady state. At this point is the point at which we are doing the step up of the input voltage. So we can see that we have a very high overshoot compared with the response in green of the PID compensator, and then we are getting a steady state, but we are reaching a steady state again quicker when we use the PID compensator. At this point we are getting almost 5 volts at the output with the PID compensator, while we need more time to get steady state with the PI compensator. And now we are going to compare the response of both converters with the PID compensator and with the PI compensator when we do a step at the output. So at the beginning we are going to have 2 ohms of load resistance, and then we are going to connect in parallel another resistance of 2 ohms. So we are going to go from 2 ohms to 1 ohm. And we do the same for the converter with the PI compensator. So let's run the simulation, and here we can see both responses. So again, the response in blue is the response of the PI compensator, so we have an undershoot here greater than in the case of the PID compensator, then another overshoot which is greater than with the PID compensator, and again we need more time to reach steady state using the PI compensator than using the PID compensator. So we can see that the design with a PID compensator is much powerful than the design with a PI compensator. Well, with this we get to the end of this presentation. I hope that you find this video useful. Please let me know through the comments section if you have any comment or question. Thank you very much for watching this video, and I hope to see you in the next one. Goodbye now.